My name is Noam Zilberstein, and my project is an under-approximate separation logic for probabilistic lower bounds. Probabilistic programs are notoriously hard to analyze, in part because the outcome is a distribution rather than a single deterministic value. This work introduces a novel technique which uses under-approximation in order to address some of the hardest problems in automated program analysis, including reasoning about termination and loop invariants. Let's start with an example from machine learning. The goal is to learn an interval 0t from examples. The output of the learning algorithm will be a hypothesis h, and the error is simply the gap between t and h. A probabilistic program can learn this concept by looping while the error is larger than epsilon. On each iteration, it randomly samples a point on the unit interval. It queries the labeling oracle L to determine whether the point is a positive example. If it is a positive example and it's larger than the hypothesis, then we update the hypothesis. First, note that it's not even clear that this program terminates. That's okay. We can still under-approximate its behavior using the bounded unrolling rule, which states that the probability of some event is lower bounded by the sum of the outcomes after some finite number of iterations. In the case of interval learning, this summation is a geometric series. So we get a nice closed form expression for the result. Let delta equal 1 minus epsilon to the n be our confidence parameter. Making delta small increases our confidence that the hypothesis is good. Solving for n, we can determine that we have to see about 450 examples in order to get 99% correctness with 99% confidence. This is very useful to know because it tells us how much training data we need in order to achieve a good result. Interval learning is a one-dimensional version of the rectangle learning problem, which is a well-known example of a probably approximately correct learnable concept and has many practical applications. We could write a more complicated learning algorithm and use a mechanized version of the program logic to automatically derive correctness bounds. To understand what under-approximation means, we have to look at the definition of the Hoare logic triples. We only require that the postcondition holds in a distribution smaller than the result of running the program, rather than the full distribution. While subtle, this results in a whole new proof system and addresses some of the hardest problems in probabilistic program analysis. Existing probabilistic logics require that programs terminate with probability 1. This complicates proofs and prevents us from analyzing important programs that may not terminate. Using under-approximation, we can analyze these programs, but as a result we can only deal in lower bounds. However, lower bounds are a powerful tool that align nicely with classical results from machine learning, as we've seen, and also cryptography. Thank you very much.